YouTubers, I received a question last week about particle in a box theorem, and I am going to try and answer that question, although I think I'm going to simplify it a little bit. I was asked to basically give an overview of particle in a box to help review what that is. So, to explain particle in a box theorem, first of all, it's quantum mechanics. So if the words quantum mechanics makes you really itchy, I would suggest that you should probably jump ship and go watch Michelle Phan or something. So, anyways, I digress. First, we'll look at regular physics. And so if we look at macro physics, you're going to be looking at stuff like a ladder on a tree, or some kid swinging, or something like that. But when you look at quantum mechanics, you're looking at something a lot smaller, and it's very different. And you might be asking, how? How can that be different? That doesn't make sense. Well, for example, let's look at this pair of sunglasses, okay? We're going to assume that these are in the macroscopic world, and in fact they are, because I'm a human, and we are giants, and we are not living in the quantum world. So these sunglasses, we can assume, are not moving, and we can assume that there is a 100% probability that they are right in front of me and that I'm holding them. But when we get into quantum mechanics has some really funny things. So basically, you can have something, and it may or may not be in a location that you want it to be at. Some of you guys may have heard of Heisenberg's uncertainty theorem, where you can know the position of something, but you can't know how fast it's moving, or you can know how fast something is moving, and you might not know the position of where it is. That has a lot to do with probability, and there are certain probabilities that you'll be able to find a particle located in a certain region as opposed to another region. And to do this, we kind of set up a box. And this box, I've got one here, and basically this box is a set of confinement, and it confines where this particle can move. I have this red locket, and we're going to assume that this is a particle. And so it's moving around in this box. Outside of this box, there is a 0% probability that you'll be able to find it. So it's reaching these walls, but it's not when it reaches the walls, it can't necessarily be located exactly at the walls. So we know that there's a 100% chance of it being located in here. So we know that there's a pretty good chance that we'll be able to find it. So that's called confinement. And a lot of times when you get into these macro-sized particles, you're going to try and get smaller and smaller. So let's see, we make the box a lot smaller, and it's about this size. So we'll put that in here, and lo and behold, the probability of finding it in this is much greater. There are certain places inside this box that you won't necessarily be able to find it. And these places are called nodes. And so it depends on the kind of function that you're looking at. Particles tend to be represented by different types of functions, and many times they're called eigenfunctions, which are really complicated to explain and have asterisks and Greek symbols. So basically, you have this box, and it keeps getting smaller and smaller, and you can find where this particle is. And you can graph it, basically. So another question that's commonly asked is about the Schrodinger equation and Schrodinger's cat. So here we have Hello Kitty, and we'll assume that it's Schrodinger's cat. So we're going to put Hello Kitty inside this box. Alright, so she's in this box. I don't have a Geiger counter, and I don't have cyanide, but in the thought experiment, Schrodinger proposed that if you put a cat inside of a box, and inside of this box there is a radioactive particle, a Geiger counter that is connected to cyanide, and you close the box off, and you can't see the cat. They know that the particle has a 50-50 shot of decaying. And if this particle decays, it can cause the alpha particles to cause the Geiger counter to go off. And if the Geiger counter goes off, then the Geiger counter will trigger the cyanide, and then the cyanide will basically kill the cat. So, we don't know if the cat is alive or dead inside this box. So, it could be alive, it could be dead, but we don't know until we observe it. And there's a 50% chance the cat will be alive and the cat will be dead. But we're going to just not observe it, and if we don't observe it, the cat is both alive and dead. And that has to do with the strange intricacies of quantum mechanics, where you have something that can be observed or not observed, and you don't really know until you're actually able to perform that function. So the thing is in quantum mechanics, your outcome is influenced by observation. And that has to do with, if you're looking at something under a machine, you chance that your observation can affect your final outcome. And so that's quantum mechanics in a nutshell. Hopefully I didn't botch that question too much. So, ask away!